Hey, what's going on, everybody? Today is April 22nd, 2024, and you are listening, watching the Daily AI Show live. And today we are talking about a new concept, fairly new, came out this month, I believe, is when Google DeepMind came out with a research paper talking about mixture of depths. And we'll just call that MOD for a lot of this show, probably just to keep things easy. And you might be thinking, oh, I've heard them talk about something like that. Well, you probably have, but that's mixture of experts, MOE or MO, we can call that. So we have MOD and we have MO. And we're going to be talking about both of those today because they're both really, really important to talk about where the future is going and how this is going to affect on-device type LLMs and stuff. But I think probably the first place to start is with number one, tell you who we have today. We have Jyunmi, Andy, Robert, and I'm Brian. And we're going to do our best to kind of break this down, talk about what Google DeepMind really just came out. What are they saying? What does this mean? They talk about routers and they talk about how tokens move through the process and what it does at individual layers. It's really important to understand this, or we feel like it's very important to understand this, because it really does give you a building block knowledge of where this is going in the future. And it definitely will impact how your business or, how you individually with your role are thinking about AI, because it's always good to have an understanding of, hey, where's this going to go in 3, 6, 9 months, 2 years, whatever the case may be? How does that impact my job? And you're going to see today, I think, how MOD and MO both are going to impact that. So I think usually I jump over to Andy. Andy, I always love your breakdowns. I don't want to put you on the spot, but do you have sort of a starting point for us when it comes to mixture of depths and what it means? Let's start there.
Sure. Good morning. So mixture of depths is a process of training an LLM to do dynamic routing of tokens. And that's been done before. The approach that was taken in this archive paper is slightly different. And so I'm going to explain how that is. But I'll actually step back, and from most of them in the audience who haven't thought about or been instructed on how large language models are architected and how they work, I'm going to give you a primer on that as well. So there was an archive paper that was put out by a fellow named Adam Santoro at DeepMind. Now, he's been at Google DeepMind in London for 8 years after, and this is important, getting a PhD in neuroscience. So now you can imagine how somebody who's a neuroscientist working in Google DeepMind is advancing the state of the art in how to train a deep neural network with efficiency and with effectiveness in mind. So thinking as a neuroscientist, he's along with many other researchers who are listed on the paper, they've developed this method of learned dynamic routing of tokens in an LLM. So I'm going to shortcut the idea by saying what I take away from the archive paper is that what they're doing is they're training an LLM on a restricted diet of tokens. And when they do that, they force the LLM to achieve its optimization. They force it to learn itself how to route tokens to the best places that can do the things most efficiently within this very large set of parameters. Okay, so in general, what this new method does is it exemplifies ongoing advancements in neural network methods that continue to increase the performance and efficiency of these things. And to put a number to it, it's faster in training to use this method, and it's also then faster in inference, about 50% faster. So now I wanted to step back and do just a quick primer. So the way a typical large language model is built, and particularly transformers, which do that's the main architecture for large language models. They have these components. And the first is the input layer, which just receives the initial data, the tokens. And let me describe what a layer is first. So a layer is a whole sort of, let's think about it as a horizontal layer of neurons in the deep neural network. And that input layer has just one job, just to receive those and pass them down to the next layer. Now, when you set up an LLM or any deep neural network, you're asked to define how many hidden layers there are. And the hidden layers just represent how many layers deep does this deep neural network go. And the more hidden layers you provide, that increases the network's capacity to form complex representations. So think about it as, in a deep neural network, we're just going to feed it a bunch of tokens, and it's going to process those by passing them through every single layer in the deep neural network that you've defined. And each layer passes what it's resolved in sort of deciding what this token is about to the next layer, and so on. So the more hidden layers you've got, the more complex the representations. Think about it like if you were baking a cake. So you have the first layer basically can only capture the data of what the components of the recipe are. And it passes those on to the next one. The next one can say, okay, here's all the ways that we can mix these things together. And my objective is to create a cake. So I'm going to deliver a cake. Now you go deeper and deeper, and it can capture more and more detail about that. Okay, this is the depth of the icing that we're going to put on the cake. Or here's the art that we're going to put on the cake. And the deeper the neural network, the more refined the definition of the output layer can be. So you've got the input layer, just pass it on to the attention layers. And each one of those hidden layers can decide, what it should attend to in the stuff that's been passed to it by the prior layer. And that's the key advance of what transformers were. Remember the reference to all you need is attention? Well, yeah, that's training a hidden layer to decide what elements of the tokens that it's just been passed are important and which are not, and which should I pay attention to. So
can I just pause you real quick there, Andy, just because I love what you're saying, but I want to make it clear for our audience, just in case they're just getting into this. When Andy's saying tokens, we input words into ChatGPT, but those are quickly transformed into tokens, which is basically turning it into math in a very, very complex, multi-dimensional vector database, right? So it's doing massive multi computations through math and trigonometry and all sorts of crazy things that we don't need to get into here. But that's what's happening. It's like, so it's encoding it with an EN, right, into tokens. And then as Andy's just talking about, I'm sure you can explain it. There's a decoding layer on the back end of that. And there's a lot of hidden stuff that happens in between to the tune of 60 different layers on the encoding, 60 different layers on the decoding. So I just want to make sure. So just in case anybody's listening, they're like, tokens. Tokens is what happens after we hit enter on our keyboard and we ask the question of a ChatGPT or a model. This is what happens to the words. It's broken up basically into math.
So in case you're all wondering, this is, sorry, I want to share. So this is what he's talking about. This is OpenAI's tokenizer. So you can take a word. So here's an example that you can click on. It takes 252 characters, which is the letters, right, and numbers and emojis. And you can see the number of tokens it has allocated. So you can see it's not exactly a one-to-one. Sometimes there's a whole word. Sometimes there's parts of a word. Sometimes there's just one number. So when you're talking about tokens, yeah, good point to that, Brian. It's not exactly a one-to-one when it comes to words. But I want to ask for an element of clarity, Andy. We're talking about layers and different layer levels. Are we talking about word vectorization like semantic association? Like, are we talking about, so this is a cat. I used to have this when I did a presentation. I had a cat. Now, a cat can be a pet, or a cat can be a feline, or a cat can be 4 legs, or a cat can have a tail. So these different layers are associations. So if I had a cat walked across the street and I want to take that input, as you call it, that the language model is understanding, and I want to understand the layers. Well, this is anything with a tail layer. I want to associate this particular word of that sentence and those other words in that sentence, because cats walk. So cats walk is a layer because animals, is that what you're talking about? Is that how the model?
Yeah, that's a great way of, you gave me a great model to clarify that. So imagine that I'm training, let's say we have 100 layers, and I got the first layer is just going to receive it and passes to the next layer. Well, the next layer can capture whether it's a cat or a dog, right? That's all it can do. It can do a classification.
Okay.
But then it passes its information down to the next layer in the training set as it's feeding all these tokens during training. And the next layer can discriminate between, a wild cat and a domestic cat. And then you've got all the different species of cats. And as you get deeper and deeper in the layers, those subsequent layers are capturing these finer distinctions in the training data. So that's the way it cascades down through these things. And yes, we're using a classification example here. And then when we think about large language models, there's a combination of things like classifications, important, semantic classifications of terms and words, but there's also context and meaning that are being captured by the LLM so that it can do these amazingly, seemingly super intelligent things in conversation with us. Okay, so the number of hidden layers is very, very large in these large language models. And typically what's done in training and in inference being where you give it your prompt and it then decides what the correct outputs are based on its training. But in large language models, typically that's just feeding all of those tokens through every single layer. During training, they even do that. They take all of the training data and they do it through a number of epochs, as they're called. Epoch is a single epoch is take all the training data and run it through the entire stack of all these layers. And they run many, many thousands of epochs in order to get the training refined down to this point where it's capturing all the information in the training data. So what mixture of depths does is it says, that's not very efficient. We're sending all these tokens through every single layer, and it's taking a lot of compute. So instead, the mixture of depths method says, instead of doing that, we're going to train the model to find the right paths through these layers, maybe even skip some layers, and go to a different set of layers. But we don't know how to tell it how to do that. So we have to train it to learn itself how to optimize the pathways through these stacks of layers in order to achieve the same benchmark performance as if we let it just process all those at very high energy expense and time. The compute required, the flops, that are required in compute to do that training that way is not that efficient. So the mixture of depths method says, okay, we're going to do something here. We're going to say, look, we're going to give you a diet. We're going to put you on a diet. There's a budget. For these layers, you can only use this many computations against tokens. And what we want you to do is to figure out how to optimize the outcomes, but living on that diet. And what that diet does, and this is a stupid analogy to real ML engineering.
No, it's good. I like it.
But by putting that restriction of the number of tokens and compute cycles that are available by layer, the large language model learns where to route tokens based on their importance, the attention mechanism. And so the method really results in an amazing improvement in the efficiency of both training and performance in inference if you've trained a model to do it that way. And that's really important to us. Why? For energy conservation reasons and for just optimization of the chipsets that we have. Like we only have so much compute power, and we want to make sure that we get the most result out of that. And the mixture of depths method achieves that through this restricted diet process, as I'm describing it. Okay, so I think that that modification, that description of the modification is enough to start the discussion. But it's one of these major advances that's improving the performance of these models dramatically.
And I want to get Jyunmi and Robert into this. I'm going to give one analogy just to pivot from this point, because I by the way, but I used Meta.ai for this analogy. I said I needed an analogy, and this totally made sense to me, so I want to pass it on. Okay, Waze, the app Waze, you would use it on Apple CarPlay in your car, right? Now, Waze is just like Google Maps. It's owned by Google, actually. So this works out well because this is Google DeepMind that came up with mixture of depths. Okay. I need to get from point A to point B, and I have an energy budget, whether that's an EV or we'll just call it gas, right? I have an energy budget. And Waze is going to say, look, there's about 4 different ways, given traffic conditions, to get to your end result. And mixture of depths is going through those and saying, here are the options for efficiency. You have so much gas, and our job is to get you to the same end goal. So the same result, quality of result. I still got to get to the location I'm going to. And I need to do that in the most efficient way possible. In fact, I have EVs, so this definitely comes up a lot on the EV side because I'm always thinking about how much battery I have, how much do I need to have left at the end, and will I be able to stop over and get a 20% charge on the way there? Okay, if we add in the mixture of experts, okay, which we've talked about before, here's how that gets even better, because what we're going to see is this combo of mixture and depths plus mixture of experts ends up being something very cool. Okay, mixture of depths has told me the way to go to the place for the most efficiency. Mixture expert says, hey, now that we're on this path, on this highway, I have deployed experts in multiple different areas. So we're going to call one of these experts the road condition expert. And so now what Waze would do, it doesn't exist, but let's just hypothetically say, Waze would say, hey, for the next 5 miles of this chosen path that mixture of depths has chosen, stay in the left lane. It was recently paved and you're going to get more efficiency out of your tires for the next 5 miles. See, we had an expert that came in on the path that was chosen through the maze from mixture of depths. And it's saying, I, along with many, many other experts, have decided that the most efficient way on this path is to, in fact, be in the left lane. Now, this doesn't exist in real life, but it gives you an idea of how mixture of experts layers in with mixture of depths and what the potential could be for efficiency. So that's that one really helped me. I don't know if it helps with you guys, but
I like that.
I'm not sure if I would say definitely is a good analogy. I love the analogy, by the way, for mixture of experts, but I feel like if you want to make the true analogy for mixture of depths, you'd have to be like, okay, there's 20 experts, you get to choose 10, and those 10 are the only ones that are going to help plan this route. Like that's like in those experts are the most efficient at it, as opposed to a marketing expert looking at the billboards, right? That's not going to be the person you would choose, right? You wouldn't choose that one. So like back to Andy's point, you're getting away the fluff, and this is about flops. This is about putting on a diet, right? This is about using operational computations that the resources, and allocating them the best use possible. I love that. That's a good analogy. Was that yours or somebody else's?
Be honest with you, I said I needed a really good analogy, and it gave me a few, and it started getting into like layers when it comes to like for a mixture of depths. Whereas like it's like a car being created. You have the assembly line and painting and quality control and customization, and that's true because that goes along with what Andy was saying. Is like we're going through this network, but that's very linear. Like the car starts here and it always goes to the next layer. And what Andy is explaining with mixture of depths is that, like he was saying with the gentleman who wrote the paper, who was in neuroscience, this is a complex neural network, and there are many, many, many. And then the Waze is very simplified because the car, it would be nuts if the car changed its pattern every 30 feet while you were driving. You were like, look, at some point you're going to have to tell me how to get to the thing. And if Waze was like every 30 seconds was like, no, go this way. No, hold on, go this way. It would be undrivable, right? So it's a very simplified analogy, but that's the way it makes sense to me. Is if you had a highly, highly tuned Waze, then yes, it would be trying to always skip roads. Like Andy said, at some points, what it's trying to say is this layer is not even important for this specific token. And like Robert, you showed on the screen, it was like 252 characters, but it was only 57 tokens. So now what it's going in is saying, okay, 57 tokens. I don't even need 6 of these layers to figure out this one token, but I need all of the layers to figure out 4 of the tokens. And it's just throwing efficiency at it so that you get the same positive, result, but you're spending a whole lot less. You said a compute power, also called flops. This will be good for our show tomorrow when we talk about all the words. So, and Jyunmi, I apologize. You've been here the whole time, and I want to get you in on this as well because I want to get your thoughts on this.
Yeah, I'll boil it down for brass tacks. The way I looked at it. So big news about this for our audience is it shows a 50% increase in efficiency. So yeah, which is huge. That means we're saving 50% of the flops that are needed to be used, right? And the concept really comes down to
somebody's echoing.
Yeah. I was just trying to check on that myself. And it really comes down to is they implemented a router, right? So that device that controls all of your data going to your Wi-Fi and everything like that. That's essentially what it is. It's a router that they applied as a technique to route the information as efficiently as possible. And it's the allocation resources, or resource allocation part of the technique that helps it learn to determine how to spend that budget. So, yeah, these are the basic three takeaways I got for it. Is one, they applied a router. Two, they've taught it to learn how to find the most efficient route for what it's needed, what resources is needed. So, like mice in a maze kind of test, figuring out how to efficiently solve the maze. And three, it's 50%. That's the biggest takeaway for me. It's a 50. That's huge. That's gigantic. And so I think what we'll see here is we will see this technique much with MOE, much with evolutionary model techniques, and things like that, and applied across the board with our different models.
I think what was really exciting about this time is people have been saying that EVs are having a problem with battery capacity and the network, and I was lamenting to my Uber driver who's driving a Tesla, who's very green, very much a hippie, and because I'm not quite sold on the EV right now. I'm like, I don't know, I think we should go on hydrogen fuel cells, but that's a different thing. But and he's like, no, the technology is gonna get better, and I would tend to slightly agree, but right now with language models, I feel like it's coming at us at all these different angles. Like we're going to get Grok, which GROQ, not Elon's Grok. That's going to make it 800 times faster, right? Then we get this one that's going to make it 50% faster. And then we have the more efficiency. So you're going to have them training on their own data, which is going to make the data sets required less. And you're going to have, the models are getting smaller. The tools that they're using to build the models, the technology, it's like everything is squeezing it down. And honestly, like they said, the report that came out just today, Apple is claiming that their next is going to be an on-device powered LLM, the next release. So if that's the case, that's what we're going toward. And so we're not going to have it cloud-based or internet-based or having to go out. And that's the exciting part. So I love what you're saying, Jyunmi. It's like all the technologies are in this MOD, MOE, all that kind of stuff is really going to make everything faster, better, and more efficient and cheaper. So,
and I was saying in our show notes that, or not show notes, but we have a show ideas channel that we use in Slack for exactly what it sounds like. And I was just saying this morning, so this is probably worth, I'll tease it, but I think it's a whole other show, is Jyunmi, you said one of the things you are absolutely looking forward to is when this stuff deploys on a Raspberry Pi. And for anybody that doesn't know a Raspberry Pi, that is what would you call that, Jyunmi? A very simple computer. It's like
it's a single board computer.
A single board computer.
It's a whole subset of computing devices, which are pretty cool. You can kind of make them do whatever you want. DIY world. Yeah.
Yeah.
And very hacker friendly. Sure.
When we get to a point where so I was thinking, I didn't get this from Meta, but I was like, what would be a good understanding of this? And we'll talk about it maybe on that full show. But, when you think about a smart doorbell, we go, okay, it's a smart doorbell, right? It's a Ring doorbell and it can do whatever. But in the near future, there will be a fully deployed on-device LLM that's using MOD and MOE that's basically running off a Raspberry Pi that is so tuned, it's using 3,000 different models at once because it's always picking the right expert at the right time for the right token. It's using mixture of depths to the whole thing. And now it's, because my daughter will eventually be, me and Robert, we'll eventually have daughters that are, dating and stuff. It's in the near future for us, and I'm just thinking I need this smart doorbell to just like when the boy answers with the flowers and it just goes, no. It's like, why? It's like, because no. The answer is no. I've already computed this 1 billion times through my little Raspberry Pi to brain, and we're at edge computing now. And I am infinitely smart with LLM, and the answer is just simply no. From 1,000 different angles, no. And the boy's just standing out there with flowers, like being the dad on the inside smiling. So anyway, that's the silly, stupid thing, but I think this will be a great conversation is to go. We've talked about edge devices, but MOD, MOE, MOD, MOE, whatever you want to call them, man, when you're talking about 50% improvement, when this stuff really gets going, I get super excited about what does that mean when any device is clearly capable. Our phones to start with, maybe with iOS 18, are able to be equally as smart as any LLM that we currently use and probably future ones on any device, of any size. It's cool.
When we get to that show, there's a very cool company called Gigantor.
That's a good name.
Okay, good name. That has patented technology that can put a convolutional neural network onto an ASIC. So, gosh, I'm skipping on the acronym. That'll be for tomorrow's show.
I don't even know a show. The shoe.
Application-specific integrated circuit. Application-specific integrated circuit. Okay. So your Ring doorbell application needs to be able to interpret the video that's coming from the thing. Well, this technology they've developed, blows away any kind of video recognition system because it makes it application specific and puts it on a chip. And so like the latency for the calculation of a detection of an object in a video, for example, to determine that it's the boy and what these are flowers, which might take milliseconds for an LLM to do that, or a deep neural network that's application specific to do that. This chip can do it in microseconds. Yeah. Okay. Because it's just all hardware. There's no software running on it, right?
Yeah.
Well, there is a kind of software running in the design of the chip. But anyway, we'll talk about that on the edge computing, because this is a tremendously powerful advance in edge computing. Gigantor, check it out.
So where else do you see this going, I guess, sorry, Jyunmi, go ahead. But I was just curious, my general question, as we're sort of getting to the end here is like, where do you guys see this going? I mean, today is specifically about mixture of depths, but again, how it combines in with these other pieces to what you said, Robert, which is like, it's not just mixture of depths. It's impressive, but it's when you combine it with all this other amazing stuff currently happening, coming at us from all different angles. What does this mean? Like, what does this mean for businesses? How would you process this right now? And what do you need to take away from it, I guess?
So I think I went over, like I said, the brass tacks of what would apply for businesses and why this is, you should recognize this. But I think we have an opportunity to explore or what I found most fascinating about this is how they applied the thinking behind the technique that was developed. Like I said, they essentially applied a router and they essentially applied a resource allocation system. All right, that's a budget, right, or a diet, like Andy said. These are not new concepts. These are things that we've used in technology, for decades, right? In various applications. What else can we choose as a novel form of what we've already experienced in other, maybe even tangential technologies, and apply that thinking? So immediately, my brain went to game theory, right? So when you think about resource allocation and finding out and choosing the most efficient route, that sounds like you're trying to play a game, right? Like games are like racing games, for example. It's finding that fine line, that perfect line, so that you have the shortest amount of time, right? That sounds like, trying to get to the end result most efficiently, right? That car only has so much fuel before it's got to go back to the pit to get, re-upped. And so that's budget allocation. So a racing game, 4X games where, you're playing like Sid Meier's Civilization, where you've got, only so much gold to spend and only so much resources that you can spend on the macro level. So I think, if not already, and it would be fantastic if NVIDIA was doing this because they've had such a long association with gaming, is to apply things that we've and techniques and concepts that we have used in other forms of technology that we may not associate with artificial intelligence, with machine learning and things like that, and apply those methods of thinking to try and create some greater result out of it. And I think game theory is a good one to try and apply.
I like it.
I think the easy one for me, to answer your question, Brian, for business, is that this is just going to make it more affordable, approachable. It's going to limit from the big dogs. Ironically, they're coming out with the technology, they're putting out the papers, and then hopefully the smaller labs, smaller outfits, companies are going to be able to use this technology to make models that are much leaner and more efficient and deployable. And I think this has been said a year ago, and I brushed it off because I didn't think it was possible, but maybe every company is going to have their own LLM, and this is going to allow for it. So that's easily to say for people like Nestle or whatever, PFG group, they can do it pretty easily because they have a budget. But in my head, I'm talking about even the smaller enterprise companies. This is going to be approachable to them in the near future. And people like Cohere are claiming to help those people build their own models, but maybe this technology, you keep on doing this, keep on having upgrades and improvements, there's going to be opportunities for groups to build models for medium and large companies, have their own on-site, on-device, not tied to anybody else language models. So get rid of token costs, get rid of APIs. It's all your own model. That's where this should go. I'm not sure if it's going, but that's where it should go.
Yeah. And I would imagine that's like with what you do, Robert, at WSI, right? Because you deal with the word just went right out of my house, but the different businesses underneath the parent business. Was it franchising? Thank you. I couldn't think of franchising. Thank you. But I would imagine we could maybe extrapolate out in the future, and you could be deploying AI solutions for the entire franchise model, but every single franchise and every single geolocation might actually have their own level and fine tuning of a mixture of experts to make sure that they're getting the most efficient. You've got the global pass down from the franchise company, but then every single location is fine tuned that to make sure they get the most out of wherever their geolocation is.
Right. You might have the casual pint language model, but the casual pint of Omaha, Nebraska's model will be tuned to their needs specifically, or their demographics or their client base. I mean, that's one example. That's a restaurant. Obviously, it won't be as deployable, but the larger concepts that more are business consulting or consumer based. Yeah, definitely. I like that idea. I'm gonna take that one.
Yeah, go with it. Andy, any last thoughts here before we wrap it up?
Yeah, it's just to me, it's astonishing. What's happening behind the scenes at these research centers, whether in academia or in the companies, and the level of sort of intellectual application to the project, which is creating efficient and effective artificial intelligences. It's just mind blowing. I'm really proud of our ability to mount these kinds of efforts, and that someone, in a lab in London has created this level of efficiency from, some insights that are about the attention and routing of tokens inside a neural network where we don't really have any way of articulating them. How do we accomplish that? It's amazing what's going on out there. We're just commenting on it. We're not building anything yet. So,
hey, but listen, that's why hopefully our audience keeps coming back, is to get, the summary, the high level. Hey, why do we think this is important? Based on our general expertise and knowledge, where do we think this is going? So hopefully you got something out of the mixture of depths, and also maybe a little bit more about mixture of experts, which we have talked about before, but how do they combine? Where is this going? Later on this week, tomorrow, we're going to be talking about AI jargon. So we've actually used a few today, like flops, which I think should come up tomorrow, because frankly, it sounds like a cool term. And what is a compute budget? What does that even mean? So these are the types of terms, maybe MOD and MOE. We'll talk about those again tomorrow. We're all going to kind of bring our own sort of AI terms and acronyms and be like, hey, we think these are the ones that you need to know. I will tell you agent will be one of the ones we talk about tomorrow because it's misused a lot. So we'll talk about all that tomorrow. On Wednesday, we'll talk about the news as always. Thursday, a really cool idea, just a fun conversation about like, what would it take for 3 writers with no staff, no whatever, to win an Academy Award. We're going to even say Best Picture in 7 years. So we're really excited about that. That's sort of a fun conversation. We'll explain where that even came from, where that idea came from on Thursday. And then Friday, we're going to do our an honest review. It's every other Friday. We do an honest review of another tech product, service, or otherwise. And so we're going to focus on Friday with Zapier Central that just recently came out. And it's interesting. How does it compare, contrast against something like a Respell? Did they just make it easy within Zapier to build more customized APIs and so on and so forth? So that will be Friday's show. So keep coming back all week. Thank you to everybody today. Thanks for our comments. Thanks, Beth, for listening in. Beth couldn't be with us live, but she was watching along. So appreciate you, Beth. We'll see you back here tomorrow. Until then, guys, have a good one.
Aloha.